Okay, let's start. While I'm still waiting. So on Thursday, we'll potentially have a delay again because there's the Whitby lecture. And just to get it a little bit personal and closer, the speaker was my teacher. One, I was already over 60 years old as a student. So the man, he's coming, was the man I listened to his formal offered courses on fracture mechanics at Harvard through Zoom in the fall of 2020. So I listened to it. He teach it in a traditional way. And I jumped up and down and I said, yeah, this is not right. Meaning, I could not accept the level at which they are happy to describe fracture mechanics. Is that clear? You will eventually see. But basically, I was very unsatisfied. To the point of, I say, lost sleep, meaning I did have a few cases where I woke up early enough in the morning and couldn't fall back asleep. Yeah. So this week you will hear this guy talking. He is. I'm not going to give that introduction until then, and likely I'm not going to say anything controversial with him. But the rest you will hear it. As we discuss fracture mechanics. So my current plan to make it, I don't know you call it exciting or not, but my current plan is to have a clean cut and we come in the beginning of section starting fracture mechanics part of it. And I think, in fact, this prevents me from saying something terribly outrageous. I plan to record it and share it publicly, since I think fracture mechanics, as I said, was never taught in the way I think that can be more helpful. So before that, you could already enjoy the idea of fracture mechanics in the sense, well, talk about brittle fracture versus ductile behavior. So is fracture of what we're dealing with a matter of fracture mechanics? Yeah.
Is this to say that we're going to have a class on Thursday that's
This Thursday, right.
Or, you're saying today?
Yeah. This Thursday, we will have the Whitby lecture, and it's likely to delay our class,
so
as last time happened.
We'll start later, and then we'll start earlier on Tuesday?
We can catch up if that's what you mean.
Mm-hmm. Yeah.
You're thinking way, way ahead. I'm just teasing, right? Yeah, we can catch up if necessary, right? Depending on how much time we lose,
Okay.
right? Yeah. So it's going to be this Thursday. I think I will be the one to, at the 2 o'clock, to introduce speaker, and then we have a Whitby lecture, and our class follows. Yeah, and I'm inviting you to that lecture for sure, as part of this whole discussion almost. So again, a little bit a personal comment. So about 4 years, time just flies. It's over 4 years ago. Upon listening to his fracture mechanics, we were both implicitly aware, gee, who is going to further work on this problem, on the polymer fracture? So it was very clear, either he has to learn polymer physics, or I have to learn fracture mechanics, right? If you want to continue, I wouldn't call reviving the subject. The subject is right there. If we were to gain some more understanding of it. So I was quite aware that either he has to learn enough polymer physics, or I have to figure out what is fracture mechanics. And here we are, 4 or 5 years later. It takes a long while to learn polymer physics. It takes a great deal of time in addition to learn polymer rheology. And speaking of that, this very dear subject of this thing being brittle, I already just posed 5 minutes ago, is this a fraction mechanics question? And today you will have a short answer for that, hopefully today. In fact, we will have short answer. And separately, the ones who worry about and try to understand that this is brittle versus ductile are people who don't blame them, who did not have a lot of insight. I didn't bring my book. Who did not have a lot of insight about what is polymer rheology per se. In particular, appreciate the idea of the fact these chains are all suffering this constraint from uncrossability. And what does that mean? So in fact, today we precisely will try to get some insight from what we learned from polymer rheology. I keep saying that that polymer rheology was really somewhat brief, right? But nevertheless, I want you to, I think at one point I did show you, it's this picture, right? Did I show you this slide? I think I did, right? So that whole thing, I just still want to insist that rheology is what I call today, rheology is mother of everything. That this movie showing that this thing doesn't shear properly, because right now it starts at about a quarter it starts to fail, right? I have shown this movie before, and this movie is about counting exactly 20 years ago when you were in kindergarten or somewhere, or whatever young you are. This was ultimately informing us to think that your dear polymer should be thought of not only of this thing, but also how they are related. You know, for example, they start to slide by each other. And the reason they did that is because they had uncrossability there, right? So, having that said, you have already learned, depending on how you do it, most remarkably, last time at the end, I was saying that the styrene 60 years ago, we learned that if I melt stretch it, and then stretch it in the same direction after I cool that styrene to room temperature, which is glassy now, this previously brittle styrene, after this treatment, this is not a mechanical rejuvenation treatment. Mechanical rejuvenation is done way below TG. In glassy state, it did something. I, of course, haven't really told you what mechanical rejuvenation, what it amounts to, what it does, other than to acknowledge it's the opposite of physical aging. And physical aging, we do know what it means. It means that the segment, all the polymers stuck even more, right? Become even more dormant, if you want to call it, become even more immobile. So rejuvenation, of course, is the opposite of that. Well, the English word says so. It's, instead of aging, it's rejuvenating. It becomes younger, meaning less stuck. Less stuck because you moved all the chains around, so they didn't have a chance to settle into a more stuck state. So in any case, today I think I'm going to try to share with you how these sets of phenomenology, whether it give you a little more insight about this, about a picture of what delivers ductility. So at the end of last time, I start to say what delivers ductility is the fact, even though I'm stretching far away, this could be, 5 centimeters away, I'm accessing all of them through the uncrossability, right? Next, and so there are a million of them. And so you can imagine, of course, two processes taking place. One is indeed, as I move the two ends away from each other, all the chains through uncrossability is displacing, is moving. So that moving, of course, amounts to having some mobility that occurs because of the external displacement. So in that sense, you go back to the fine concept. As I separate the two ends 4 or 5 centimeters away, I'm also separating each molecules that way. And the only way that happens is that molecule is moving then. So that particular molecule is moving, indeed. But there are many other parts that's not moving. Which is, you need most of the, keep in mind, when you are trying to stretch something and change its shape to this, that shape change means everything has to move. And to achieve that, according to Eyring idea, is to gain enough mobility. So as you try, so in this process, as you try to draw, what usually we use engineering, as you try to draw, you are starting to gain mobility. So if I plot mobility like that, the stress increases, mobility increases, they are going hand in hand. But it's crazy, I should draw a third x, which I can just share with the third x. I can draw a third x, which is what? Stress increasing, mobility increasing. If you like, the tension, chain tension, let's call it CT, in that black chain, for example, is also increasing, right? This we can agree on. Okay? We can agree on 3 things. Nominally, my stress is increasing as I stretch more. That's just a boring stress you have to get your curve. But we know through Eyring idea, or through the fact that I am displacing, I am increasing my mobility everywhere. But you need a lot to have this shape change. You need most of the segment to participate or to have enough mobility. And that hasn't happened yet, because it turns out, as I said, the best example is still what we have to appreciate. Your polymer is a coil. It's not arranged in the chopstick form. You see, if it's arranged in the chopstick form, then every chain will move as I stretch. But it's a coil. This bloody coil. When you try to move, many parts don't move at all. So the end result is you stuck there. You are unable to achieve the shape change unless you can wake up most of these parts of the chain. So as you try to do that, the tension in any given strand is building up as well. So the question is, can you reach enough mobility and yield before you build too much tension that will cause what? Naturally, that could cause, for example, this black chain start to slide away from the blue chain, for example. Because this force in the chain cannot just build up without a balance. It's basically eventually you reach a force imbalance. So that's the proposal. So the proposal is that at high temperature, remember this hypothesis that says you can go like that, and the other one says you can go like that. That's the brittle stress. I know I should switch the color, but I like the red to mean hot. But so basically you have the brittle stress versus yield stress. And this is the brittle ductile transition point. So I'm happy to suggest, or I'm content to say, oh, it's just a small improvement beyond what we previously explained, is that when the temperature is high enough, the mobility is easier to establish. So it turns out as I draw more and more, I could create enough mobility because it's warmer. And this is, as an activated process, the thermal energy is always important. So at higher temperature, you have a better chance of activate and mobilize. Before what? Before you build so much tension that chain pull-out will take place. So that's why you have ductility on this side. And conversely, brittle failure just means the network falls apart through chain pull-out. So it's not derived. In other words, I'm keenly aware what we're doing. We are merely trying to have a molecular level interpretation of what happened. We're not even predicting what this point would be. We are merely saying, if it's brittle, remember the iron idea, M0. If it's brittle, it's because you no longer have the supply of stress. So I was trying very hard to make you appreciate iron idea is insufficient. Iron says, give me stress, I can always make your having enough mobility. But it turns out a full story must be iron plus another theory, a structure one, right? Basically, the structure theory must say when you no longer have stress. And the moment you no longer stress is when you have pull out to cause breakdown of the network. I meant to break down of the chain network. I meant to do one exercise, but I forgot to assign it to you. So what I'm speaking about is all worked out in a paper 2014. I haven't uploaded this paper. I thought, quite interestingly, I thought I should give you this paper, very lengthy paper. A few people bother to, it's hard to read and properly hard to read, but not after I give you the basic point of it. But my thought was you can upload this paper to ChatGPT and ask ChatGPT to summarize it for you and see what points you have. You can, that ChatGPT tells you. I was doing something equivalent to that and realized ChatGPT is still not up to the point to be able to really identifying what the essence of it. So I think it's probably still useful, since you will get the essence of this today verbally from me, but you can compare notes with what ChatGPT will do based on the PPT I gave you. Yeah. So let me repeat, yeah. It's a very profound point, right? So the point was, what we previously are content is to have an explanation for why a polymer can be ductile. It's through the activation idea. But anyone who carries such an explanation will look away from the fact if you just cool a few degrees, the same polymer turns brittle. Get it? So that theory is so incomplete that that today we realize the reason it's the iron idea alone is incapable of explaining brittle ductile transition is because it always assumes the stress is there. To complete the full picture, you must add another theory that tells you when you no longer have stress in the iron expression. And that theory is what I'm speaking about now. In short, what delivers the stress to iron is the chain network. If the chain network falls apart, you should not use iron anymore. Then that's exactly why you identify the validity of iron concept, right? Do you all have that? Do you understand what I mean here? In other words, in absence of what I'm speaking, the iron will always say, give me a polymer, I can tell you it's ductile. And it's remarkable that we can be happy with that explanation, knowing that the same polymer can turn brittle. And now I'm adding, after figuring out the answer, I'm adding, oh, here is the problem. You need to add another theory to explain when you have stress, when you don't have stress. When you don't have stress, of course, it's wrong for you to apply iron idea because there isn't any stress. And there isn't any stress when the network falls apart through what I call the chain pull-out. So in that sense, it's now iron theory that tells you why you have ductility. So what tells you have ductility or not? Or what is the driving force for ductility? What is necessary? It's the network. Exactly, the same thing. Whether the network is intact or not, is robust enough or not. So even though nobody is able to derive this description, at least we now have a way to rationalize, how this. It's an improvement beyond just applying iron. As I said, iron is frustrating because it wouldn't tell you, it wouldn't deal with the fact that it can turn brittle. And it's not sufficient to just apply iron because that's too cheap, right? Because the hard part was indeed what delivers that stress. And quite naturally, which we are quite aware through rheology, there are a million layers, and the connectivity through uncrossability was necessary, or structural integrity was necessary. Naturally, if one chain pull-out leads to the next chain pull-out, leads to the next one, which is what you see when it breaks, then of course you start to lose your ability to draw this network further, which is necessary for the mobility to arise further. Eventually you have flow, so-called plastic flow. So I'm running out of, so I guess I will let me try to, this is old explanation by now. It's over 10 years old. But we continue to have improved understanding about it. So today I can roughly say the following, that remember this hypothesis, or usually there's I'd like to add another one. So there are 4 people here. This hypothesis claims that there are independent breaking process and yielding process taking place at the same time. Whatever lower stress wins. That's the translation of what we knew 10, 12 years ago. The spirit of it is not entirely wrong until you reach to the molecular picture, which is what I have been talking about. There is this process of building up mobility, which is toward reaching, which is a process for yielding, adding more mobility. But concurrently, you're also building stress, which building tension in the chain, which eventually could lead to breakdown of the chain network. So these 2 things are indeed concurrent. I wouldn't go further by saying that that the lower stress wins, other than to say simply that on this side the network does not break because it's easier to achieve activation and mobilize. So there were some more complications. I think I would probably prefer to reserve it to for anyone interested only, for you to read the chapter 6. All the details are described. For example, as you go to warmer temperatures, it should always be more ductile, according to this scheme. It turns out we can show the opposite taking place. In other words, the brittle to ductile transition can be reversed, and ductile become brittle again as you warm up the temperature. So this is getting us a little into another layer that I don't think I need to talk about it here, because I may run out of time. Let me tell you one part that you already should be intrigued by. I mentioned this as one of the 6 factors. In fact, this is a factor that was only discovered after we had the picture. In other words, this is not a widely documented piece of effect. Let me explain this effect one more time, right? You bring your PMMA to 60 degrees, which apparently is above BDT, okay? So you are down here. You have enjoying a ductile PMMA, okay? So at 60 degrees, it's warm enough, it's ductile. You add a few percent of a plasticizer or solvent, a small molecule. Generally, adding such a small molecule plasticizer will lower the TG, so mobility will improve, generally. So according to any traditional view, this added processor should make ductility occur even easier. But the opposite was found. Adding a few percent, this ductile PMMA turned brittle. So this is really contrary to any common sense there is, or the traditional view of brittle ductile behavior. So what's the interpretation? well, rather, how we within our current framework, how we understand it. Well, you can so the reason you have a pull out is because the chain tension has reached the level that we call chain pull out force. So it's a certain amount of tension in the chain you must reach before sliding can occur. The effect of the solvent is now interpreted as lubricating that interaction. So the chain pull out become easier. So that's the interpretation. Let me just say also one more part about the pressurization. So why pressurize your glassy polymer, make a brittle polymer ductile? If you recall, I showed you the compression of styrene that's ductile, right? And at that time, I mentioned that compression is like adding a pressure. So put everything together. What pressurization does is, so of course, it's not a prediction, but it's an explanation. What pressurization does is, instead of lower the threshold for pull out, it increases the threshold for pull out. So this is pressurization effect, and this is the solvent effect. So in presence of pressure, it will take more chain tension build up for pull out to occur. By that time, activation already occurred. So you yield instead. So this is an explanation of why such effects could be understood. And also, we could come back to the next effect of melt stretch, pre-melt deformation, right? For example, that I showed you, this geometrical condensation. What does that do? So it was weaker in the perpendicular direction and stronger or stronger, meaning it turns something from brittle. So the first thing, of course, is this melt stretching down in the so-called, we could have a habit called a fine deformation, meaning in the limit of very fast, produce this geometrical condensation and dilation. In other words, since we said the ductility is delivered by network being strong, we have changed the network. We have made network more efficient in this direction and less efficient in this direction. So you can go into a little more detail that I don't usually. Of course, in the extreme limit, that's the chopstick limit. So you can prepare your network now. All the chains are straightened more or less. Then all the chains will just undergo displacement. So you can easily. So basically, there is just for the I can sort of just flash. I know. probably necessary for me to flash through it. So just to give you wow, take this long. Just give you a more presentable story. So basically, this is the depiction that's a little bit better than handwriting. So So basically, we recognize it's a network, and there are other things that's now moving, and the network is stretching to cause. So basically, what I depicted is the red chain is moving, and that will bring the green chains to move with it, but the black green chain segments. But the black segments are not are still dormant, are still immobile. So you can just imagine as you draw more and more, you bring more of the population into having mobility. And the effect of what am I doing? So I was just trying to indicate using this diagram. So basically, what happens is if you look into the cross section, then these gray ones are activated, the black regions are still not activated. And right, I'm drawing the z direction and now looking to xy direction. And the ductility is a process of increasing that gray region until it all touch each other, which means where everywhere is mobilized. So we once even had a joke, this is the true tube model, because it's all surrounding each chain, like a tube, but borrowing that word. So so with that picture, you can really explain. For example, this is a summary of that. So for example, what male stretching does is it brings all the chains closer in the pre-stretching direction. So the job of having the gray region start to touch become much easier because they are all closer. Okay? And the rejuvenation, so it turns out it's just a two-face of the coin. On one side, you have the network struggling very hard to activate, to make it ductile. The other part is the segment all slipping, in dormant state, because they are in the glassy state. So it's just these two things going on. If I'm more dormant, then you better do a harder work to wake me up. So the effect of rejuvenation is now all the segments are only half asleep instead of asleep. So it's much easier to activate, and the physical aging exactly does the opposite. So it's much harder to activate. So that's a better, a good way to draw it. But let me get into a small part of the more. It's like a byproduct, but this is actually turns out to be the most essential and important part of it. I could begin by, okay, so let's do it on the notes here. I see the trouble of, yeah, so today I'm going to try to extend this as 14, so it's hard to always start with a new one. So let me try to, if I call this according to our outline, we are still at the topic 4 of brittle ductile. In fact, we have moved on, so mostly verbally, I have moved on to so the speed 2-4 is brittle ductile transition we have been talking about. And then B5 is about crazing that I think I will skip. Basically, it's another very important feature, but I'm going to try to skip most of it. Basically, when you stretch a piece of glassy polymer, very often you see some cracks development that we called craze. And generally, the literature had some wrong impression saying that the crazing is always the precursor. Gosh, always the precursor. Oh gosh, to fracture. The reality actually is more complicated. But in our picture, we all understood that this crazing, which is it's truly some internal breakage of the sample. The sample has achieved some separation inside, and this could be a submicron, so this could be just less than a micron in size. And in our language, then of course it amounts to some breakdown of the network. So if you like, it's localized a breakdown of the network. And part of the reason I'm skipping this is because we're running out of time, but also this remains a poorly understood phenomena. Because what happens is you ask if this is, the crazing is where weakness occurs, so it has a little crack happening. And then you ask, why it doesn't craze here? Why it doesn't craze here? And the only hand-waving explanation you would say is, how come somehow this network is not, in terms of strength, is not uniform? Some parts are simply weaker than others. Then I'm running out of language because that weakness is not at the chain level. Then at some mesoscopic level, we don't understand why the thing somewhere is stronger, somewhere is weaker. And that's why I'm leaving that part out. The part we will talk in detail is this part, which eventually will be related to the problem of fraction mechanics. So here's the basic task we are trying to. This was okay. You can probably tell me if your ChatGPT can do better than what I explained so far. Meaning, let ChatGPT read my paper and have it say what it says. I tried my best to say that it's about, ductility is about having a network that delivers the stress that can mobilize it. If temperature is too cold, the job cannot be completed by the network because network will see itself building too much tension and they fall apart through chain pull out. That's it. And that's why you have this side brittle, this side ductile. Yeah? And, of course, this point is what is called what I call it, Goldilocks temperature, right? So if I teach this in Europe, I cannot use the Goldilocks because they don't know what it means. I checked with them. The Goldilocks is our 3-bear story that we give to our kids. So it's a just right temperature. At that moment, I perceive, in fact, that's how we perceive it. It's exactly Goldilocks. If it's hotter than this temperature, you have no trouble activating and get yield. And if it's too cold, you cannot do anything. It breaks apart. So that temperature is just the temperature at which the network was marginally able to complete the job, and is also the point where the network is about to fall apart as well. Don't ask me why that point exists, but we already understand how these two competes, right? Because you build up tension, as you march on to achieve ductility. When it's too cold, it cannot happen. When it's warm, it can. That's it. We're not deriving it. We have an explanation of how this happens. That's all. So, let me persuade you to think a little further. Can we have a sense at this Goldilocks temperature, you have a stress, right? If you like, it's the point where yield stress is the same as the breaking stress or something like that. Basically, it's a point where mobility is achieved. And can I describe this stress in some fashion in terms of the idea that the stress that I measured, which is the resistance of my sample to the external deformation, can I assume that it all comes from the network resistance? If it is, then I can suggest that there is area density, let's say called chain network, Cn. And then each chain is reaching the force for pull-out, right? So you go to that critical moment, build enough force, you have to go to that particular transition point. And that's where you're just about to have the sliding, which let me characterize with the tension of Fc. And how much resistance it contribute? It contribute it's area density. So let's consider the limit. What was 6 chains? So this is the fiber limit, chopstick limit, right? The area density. Each, let me try to make sure I did it right. Each chain is coming across to your cross section only once because of the chopsticks, right? I don't know what else have a color. So that's the chopstick limit. Each chain come across only once. That area density will be 1 over the cross-section of the molecular cross-section. You don't have to remember it. We once learned that molecular cross-section is packing length times cone length from back some long time ago. That's the fiber limit. Your polymer, the one that I break several times, your polystyrene, or any glassy polymers, they exist in a coil form, not in the fiber limit, which means, for example, they come across 6 times instead of once. So wasting the area, because it's just a coil. It only bear load once, but it crosses the plane 6 times. So we can do this exercise. We already know the reason it can fall 6 times is because this strand, where do I draw this? This strand is a Gaussian coil. Let's call that RST, stands for the strand. And then the area the density of such strands we once derived it is related to the size of this strand as the end-to-end distance of it. If that, I can continue this expression. So what I will do, I know the answer, so don't ask me why I'm doing it, because I know the answer. So I will do this. I will multiply a phi and then divide a phi. I will multiply a FB and divide it FB. So let me explain. First, I have already defined what is phi. That's the fiber limit. You will see the purpose. You don't see it yet. So let me just manipulate this, and you will eventually see the result of this. And what is F? FB is force to break a chain, to break a CC bond. You know, it's typically in the 4 nanonewton range. Remember, it actually depends on the time scale on which you look at it. We covered that in rubber elasticity, in the rubber rupture part. So what I have are 3 things. I kind of want to say I did this one for you, but let's do it again in case. What is this phi times B? Times FB. That's the theoretical strength of your fiber. I think we did it once, but I can do it again. Because I always insist that this class, after you're finished, is to be able to carry out such simple calculations. Let's do it. It's 1 over P. I'm going to write numbers. P generally is something like 0.2 nanometers, okay? And cone length is generally 1 nanometers, okay? So let's do it. So it's going to be 0.2 nanometer squared. And on the top, I have 4 nanonewton. Yeah? This gives me 20 gigapascals. I'm sure I did it second time. I think we did it once. So that's sort of the theoretical limit of your polymer fiber. The best fiber we can achieve industrially does reach something on the order of 10. So it's getting very close. It's actually reassuring that this estimate is good. Meaning we're off by a factor of 2. That's really quite impressive already. So that's the fiber limit. Let's look at this ratio. It's a ratio of 2 area densities. Remember, phi is the ideal limit. That's as dense you can pack the chain, right? Each chain just occupy its cross-section once, and it starts to bear load. That's the most impressive theoretical limit you can get. And let's look at this ratio. What is this ratio? Well, by definition, it's a ratio of by definition, it's a ratio. I'm just plugging in cone length divided by r, the size of the strand. You know what that is? It's related to 2 things you have learned. One is how much you can stretch this coil. Why? Because we once learned how much you can stretch the coil is the size of this coil divided by this original, right? Initially it's like this. You're going to try to straighten it, and that's nothing but but realizing that this is not, if you want to think about in terms of, there are so many ways, but think about it in terms of ends, st cone length, and bottom is square root of an st cone length. So of course it's the square root of an st. Well, square root of an st is the size divided by cone length. So I proved at one point that's that. And secondly, you also learned it, that how many chains falls back and forth onto a given plane is determined by, we once worked it out. It's, of course, the number of chains. The area is the size of the coil squared. And Q, if you remember how many of them are there. Let me try to make sure I didn't miss anything. Basically, I'm trying to recall for you that the number of crossing that you have is the same as lambda star, and therefore this is also 1 over q. And for example, when you have 6, that's exactly how much you wasted. You wasted by a factor of 6 of the area if it falls back and forth 6 times. So yeah, I guess I just don't want to go back to the I think this formula is, I don't think I did it right here. Oh gosh. If you recall, what we did was, let me do it right, was there were n chains. Each chain passed through q times, because it's back and forth, And each time when they pass through, it occupies S amount of area, and that area is R to the second power. And from that, if I recall, this Q is roughly RT over packing length, and S is packing length divided by times cone length, and therefore I have Q. So I just derived it. I showed Q is RS divided by cone length. So that's what I had from the percolation model. So I have a geometrical way of explaining to you how what you are encountering. When you have a glassy polymer, it's in the coil form. It forms a network through uncrossability such that the strand has the size of R as T. Then that network has the density given by what I showed you related to the size of this strand. It's not efficient compared to the fiber limit by a factor of Q, which is exactly how much you have to stretch to straighten it into chopsticks. So just conceptualize it. So this is how I describe geometrically what happens when you have this polymer that's not in the fiber form. Of course, we're not in the fiber form when we make a sample like this. We're not spinning fibers here. So let me speak a little. Okay, I see my time. Can we take a minute break, and then we'll come back to explain what this factor is. The end game is to estimate what this number is, and proceed from that. So let's just take a very quick break, so that. Questions on this? So this is the only little math there is. I'm trying to do both the math and the conceptualization behind it. I don't have to repeat, but basically our goal was to have a sense, can we prescribe a formula for what this stress level should be. And the assumption was the network is what is resisting the stretching. So all the stress is coming from this network. So we're very much borrowing what you learned in the previous semester, rubber elasticity. What else? What else is there? That's why we're saying rubber elasticity is the foundation of all polymer physics that traces back to the 1940s. We're doing nothing different. Just think about this network. Wrong or right, that's a separate question. At least we get to entertain the question of what if I perceive these strands are resisting the stretching, and by providing a little, as you stretch, the tension build up, the stress build up, hand in hand. And we're only considering the last moment, which is a breaking point through chain pull-out. So it's in that sense, I have specified that we give the symbol of chain pull-out force. Having said that, I'm going to normalize, or I'm going to have a sense of how much is that force by taking this ratio, right? So we already roughly know what is the force to break. And of course, this force that I just introduced to have, it's basically, you can call it, oh gosh. Sometimes you find you cannot speak and write at the same time. Threshold force for pull-out, right? For chain pull-out. Of course, we don't know how big this force is. We really don't know. We really don't know. In fact, we're about to know a little better through, who is there? Basically, mechanochemistry. We're having some idea about how to do it right. Through mechanochemistry, maybe we can learn about how much force is involved to reach the point of pull-out. But I remember once quizzed you, this polystyrene, if you ask 100 polymer scientists in the world, 40, 50, whatever number, a large fraction will say it's transition, right? That's break. And obviously you heard what I said. It's all pull-out. Mechanochemistry will give us the answer. In other words, I'm saying that the pull-out force is smaller than the braking force. So let me try to orient you in two ways. We already know where we have it, here. We already know, you see, I break down this stress that we are estimating into three parts. We already know this middle part is 20 gigapascals. Your PMMA only shows 60 or 70 megapascals, not 20 gigapascals. Which by definition means these two factors each are much smaller than 1. Well, sorry, I think I jumped. I jumped, meaning, let me rephrase it. Sorry for that jump. Let me rephrase it. There's no question that this is smaller than 1 because I just showed you so. In other words, it's a matter of how long that strand is, right, by definition. It actually goes as 1 over the size of the cone length, if you like. You know, it could be 1/10. That's really a poor coil. Fall back and forth so many times without occupying the area without loading. So can you keep in mind? So this could be as low as 1/10. I don't know, maybe. But basically, let's move on and to do what? And to ask experiment to help us. Because the stress at this point is possible to determine, right? If you're patient enough, you prepare 10 samples at 10 different temperatures, you'll find that point. And Vincent, very active researcher at the time, in the 60s and 70s. In 72, he tabulated, and somebody subsequently completed that a little more. He tabulated this brittle stress, or this stress as brittle ductile transition. And he plotted as a function of phi, literally. Different polymers, here you are. Here. Okay, I'll just rewrite it for you. Different polymers have different P. So it turns out, he had a dozen polymers determined in terms of its force, and they happen to spread over different, because of the different packing lengths. And so he got 10 points or dozen points. Amazing, linearly. You should be amazed by that. It's linear. It's amazing. 72 result. Every bloody person on earth knows this result. And why you plot as phi? Not because you know it was in the fiber limit, but it's perhaps influenced by the fact they think it's all chain breaking. Because phi is a sense of the breaking of the bond, which occupy the area of each bond. So that's how they plot it that way. Now, let's see what in 10 minutes you learned about our theory. Let's see what our theory says. So let me rewrite our theory. And this is the part that did not get really resolved until a couple of years ago. Remember, I said this theory was built 10 years ago, but there is a part. So what happens is once again, I'm just going to leave that part out. I'm just rewriting this, huh? Phi divided by phi. Okay? Now, the rest is amusing, right? The data told you they are proportional. Amazingly. Which means what? This whole thing is a constant. In fact, today we understand this whole thing is constant because each is a constant. So let me explain. This ratio, it's basically cone length divided by the size of the strand. Which is 1 over Q. This packing model says, or give us the sense, the size of the strand in other words, basically, if you recall, we're trying to calculate how many strands are there. And if there's enough strand, you can make how many back and forth are there, which is Q. And we had a sense the Q is reaching a constant, is some number, it could be 5, could be whatever, is when you have when you form the network through uncrossability. And this suggests that the strand size is proportional to the cone length. In other words, this number by percolation model, it's by construction it says it's a constant. And the more striking part is really for you to imagine that this pull out is constant. Is that possible? Well, we don't have a theory for that. What we have is the following idea. So I think you saw me draw this 10 points, but I didn't really ask you to appreciate that that this is all done at the brittle ductile point. So they all involve very different temperatures. All involve different temperatures, and they are all below TG. sufficiently below Tg. I don't want to use, I don't want to use this because it's not numerically true, right? So basically, well below Tg. So you can imagine the chains are all deeply embedded in this glassy state to the point, I don't know, to the point that how much force to pull them out is no longer dependent on what temperature you're doing it. Well, it's done at the BDT temperature. And basically, we have a result that's probably too good to be true, that we don't anticipate this pull-out force to be constant. But by looking at the agreement between this expression and the experiment, we are deducing that it's a constant. Moreover, if you can plug in some reasonable numbers for this size of the strand, you make a guess, something perhaps reasonable. Roughly speaking, about a tenth of it. Then you can compare with the data and suggest what this F would be. Right? So that was what done 10 years ago. So we have our theory, which is this expression. We have our data, which is this experimental information. You plot phi as a function of stress. This prefactor is this factor, whole thing. And if you assume that this is, of course, is unknown because we're doing it at the scaling level. We cannot determine the so-called prefactor. But if you assume it's reasonable to think it's about a tenth, then it turns out this F is also about a tenth of the braking force. In other words, for example, we estimate this to be about 3 nanonewtons, 0.3 nanonewtons, which is about a tenth of the braking force. So at that time, we were not doing fracture mechanics, and we were indeed naive to think that your polystyrene, your PMMA, your whatever glassy polymers is without flaws. In other words, we were really comparing our, call this what? Inherent strength. In other words, what exactly is the strength at that point where you can where you observe the braking to take place. And we compare this inherent strength, and now I should switch it to inherent strength, call it inherent strength for fracture. And in some sense, we compared with the observed strength, which we should really call it nominal. Meaning, is what you observed. So let me try to explain the most I suppose the most interesting point. Historically, we made this. I hope we made this attempt to explain what should be the stress level. We are not aware that people So let me try to back off a little bit more. You get your polymer, and it's brittle at this temperature, right? Goldilocks temperature. It turns barely ductile. It's about being brittle. And you measured it, and Vincent measured it. For example, let me just try to give you this. For example, your PMMA showed a stress, let's say, around 60 megapascals, okay? And PMMA you can calculate because we know the P. We know exactly how much is phi. And we don't know what is the size of the strand, but we made some kind of arbitrary estimate of that. And after that, I concluded that the pull-out force is all the same. It's all about 0.3 megapascals. So that was the history. We are not aware that when you measure 60 megapascals for PMMA, we were not aware anyone would complain that 60 PMMA, 60 megapascal for PMMA is really too low. It's not what you should see, that there are flaws in it. So let me try to be as patient as I can. We observe PMMA and find this to be 60 megapascals. Okay? I was not aware at the time that the community, if you want to say it, perhaps think that this 60 is not, it would be much higher than 60 if there are no flaws. Your nominal 60 occurred because there are flaws. Flaws such as dust, bubbles, some scratch on the surface, anything of that kind. So let me try to make that connection for you, right? I think once I mentioned it to you, and I think I need to close that loop. So on one side, indeed, we were not trained in how fraction mechanical think about braking. So indeed, we didn't know that there is the possibility that this 60 is much lower than the inherent strength, okay? If I knew it, I would not have compared my formula with the data. Do you follow? Because my formula was supposed to apply only in the limit of no flaws, you see. You see. You see the point. But because of our ignorance, we thought that it's reasonable to compare the nominal strength with our calculation. This comparison is reasonable only if it is true that this nominal strength is true only if the flaws are not present, right? And this, remember, this is the moment I also mentioned. So I have a kind of a very mixed reaction to this. This is the time when we propose this picture to understand brittle ductile transition. It's proposed in a proposal where one of the reviewer rated F and asked me to learn fraction mechanics. So he got one part right, that is, I should look at how fraction mechanical people think about it. Right? You see, I shouldn't just directly compare my theoretical strength with nominal strength. That's true. That's true, okay? However, what is not true, what is terribly wrong with the reviewer, is that the phenomena of brittle ductile transition is not something for fracture mechanics to answer. What fracture mechanics answers is if you have flaw, how the strength is lowered by the flaw. It cannot say, oh my God, meaning it does not, no place in there, because the fracture mechanics is just dealing with the sample being brittle. So of course it's not dealing with the question of how come I warm up a few degrees, it turns ductile. Are you with me here? It's okay if you're not, because you haven't seen the full picture of what fracture mechanics is, but I already told you what it is. It's just worrying about if there is flaw, how my strength is lowered by the flaw. So why I say this much to indicate what? To indicate the following, which is absolutely essential, because my next statement is the reason we eventually go to talk about fracture mechanics. So let me say this very clearly. As I review what we did, as I admitted, we were comparing our theoretical expression, which of course assumes no flaw. It's a perfect network, perfect meaning in the sense of what we captured. And we were comparing this comparison with nominal strength is meaningful only if nominal strength has no, or the sample has no flaws in them, right? So now forward to about 4 years ago, we start to learn what fracture mechanics is, which is to perhaps blame that this 60 megapascal is too low compared to what you can achieve theoretically. And I would say perhaps there are already enough confusing discussion in the literature that speaks about, where do I have it? That speaks about this 20 gigapascal. That is the fiber limit. That, of course, is not the strength of your polymer, because we know these two factors each could potentially be much smaller than the fiber limit. So, having learned that throughout history, we still think that this 60 megapascal may be really much lower than the theoretical possibility, I wasn't so sure. In other words, when we are so how else can I say it? I can say it any way you wish. Basically, we took this nominal strength as if it's the true strength. But the true strength of a reading from the experiment, the true strength from your experiment would only take place if there's no flaws. So I know I still haven't really said it right. What I want to say is we had a feeling when we were comparing our theoretical formula with Winston's result. We had a feeling that perhaps each of this factor is a factor of a tenth. In other words, if so, then my theoretical strength will necessarily be weaker than this fiber limit by 2 order magnitude. For the because this estimate chose a very skinny fiber. In other words, let me just make sure you appreciate what I have here. This fiber limit of 20 gigapascal was choosing packing length to be 0.2 nanometers. If you choose that of styrene, it will be a factor of 2 smaller, so it will be 10 G. Okay, so it will be 10 G, and if you multiply 10 G by 100th, you get 100 G, 100 megapascal. And 100 megapascal is more or less what the styrene's nominal strength is. So here's the value of this exercise. We made an estimate where we don't know the prefactors, but by our guessing, we have reached a conclusion that your dear glassy polymers strength is what Vincent reported, implying that there are no flaws large enough to reduce, to give you a weaker strength than what you observed. I'm of course wondering whether I need to repeat any of what I said here. For some, no, but for others, I don't know. In fact, meaning, so let me try to recap. Basically, we have an idea that this we can account it for how much stress occurs through how this network resists, just like what we do in rubber elasticity. So obviously, rubber elasticity, remember, its alternative formula for rubber elasticity is of this form. It just directly involve the area density and how much force per load-bearing strength is doing. And then we find that this can be written in this form, and we know the theoretical limit for a fiber with confidence because all the numbers are the structure is the ideal limit. And then basically, if you have a feeling that each of this is a tenth, then you end up estimating your PMMA to have a strength of 100 megapascals. And the experiment found it's 60 megapascals. Very comparable. So you say, Jesus, what are you talking about? How do you know this is a tenth? How do you know this is a tenth? We absolutely don't know. As I just said, mechanical chemistry may get us to know in the future. But how do you know that, let alone this simple way to calculate the stress, how confident are you that this is such an oversimplified view of calculating? How can this be all correct or not? The only thing I can say to you is if there's no this experimental data, my hands up, I surrender. I says, I'm just trying. I don't know what else. But miraculously, in fact, we didn't, sort of, it's not we're fitting this, right? We proposed this formula and then find, gee, the experiment it showed this straight line. And I indicate to you why this is so, because this density and that density is proportional to each other. So it's just a... So So this little exercise going beyond explaining brittle ductile transition, moving forward to estimate this, as I said, how good it is, nobody knows. And how do you know it's 1/10 here, 1/10 here? Nobody knows. But since I speak to God, so I know. So convenient sometimes, very convenient. Or it's actually very trivial. You just assume each is a tenth, then you end up having a result that this inherent strength is comparable to what you observed. So what's left is whether this assumption is correct or not. Right? That's all that is left. And if you think this is, if you are confident this is about right, that I can assign a tenth of it there, and I can convince myself this whole way of computing for this stress is okay, then I reach a conclusion that don't blame fracture mechanics. It's not a fracture mechanical phenomenon. There are no flaws. There are no flaws of large enough size that has affected the apparent or nominal strength relative to what theoretical strength could be. I think I'm repeating. And that's a big deal because we thought this thing, or at least we don't know. Let me be careful. We don't know that this 60 megapascal for PMMA reflects inherent strength or not. Let's keep it as simple as that. So there will be one. So we will move on, describe a little bit about semi-crystalline polymer, and then we'll come back to fracture mechanics. And at one point, which was why we're looking at fracture mechanics, we will answer the question by experiment that this 60 megapascal is indeed the inherent strength. This is coming from experiment. It cannot come from theory because these two prefactors, there's no way you can determine them. We can live another 100 years. Maybe AI can do it. I'm doubtful that we can compute from the first principles what would be the force to pull out. That may take a while, and we don't need it. Meaning, the logic was, if you can show that this is theoretical strength, then everything else falls apart. Meaning, for example, then it shows probably the pulling out force is indeed very weak compared to breaking the chain. In glassy state, at the brittle ductile transition point, somewhere deep below TG. Okay. Yes? No, you didn't. I said, okay, hold on. At the very end, I said we will eventually have an experimental proof that this 60 for PMMA is the inherent strength. I have not shown you any way of doing that. Without doing that, I don't think we can make that conclusion right now. Oh, sorry. What I mean is, okay, so how do I put? What I mean is this has been, if you like, what we thought is the case. Meaning, prior to us coming into this, that's the whole point, right? That's the whole point of also, I think it's also the whole point of the reviewer's confusion. Meaning, if he had not had this picture in mind, that we blame flaws for the brittle failure, he would not bring in the fracture mechanics into the story. But then he confused how fracture mechanics can solve the brittle ductile problem. Of course you cannot, because it's so, I use the word laughable, it's so far beyond wrong. It's not even wrong. Have you heard that word? I think Pauli said that. It's so outrageous wrong, it's not even in the category of being wrong, actually. Let me paraphrase it. And so it's quite outrageous. That is outrageous. It not only shows he doesn't understand what brittle ductile transition means, it also means he doesn't understand what fracture mechanics means. I mean, that's very scary. Chain network. Yeah, sorry, I just verbalized so much without writing them down. Yeah, chain network, CN stands for.
And CP, can you remind me CP as well? So chain network.
Chain pull out.
Chain pull out.
CN is just the force needed to stretch the network, right?
C what? Which one?
Would
FCP. Or FCN. Sorry. I had the ones I said FCT stands for chain tension. I'm sorry. I just verbalize so much. I know you become victimized by it now. I'm trying to save the time to write it. So yeah. So I was right. So there's chain tension we call CT, and reaching a point of chain pull out we call CP, which is the upper bound of CT, FCT, right? Yeah, sorry, a lot of notational thing. Yeah, so I was, here you see, I was trying to basically saying it reaches that point when the pull out occurs. Okay. Yes, please, John.
I was just wondering, so not more of the methods of the class. What day of the week would the final be scheduled?
I think there is a finals week, right?
Yes, what day?
I have no particular preference. Depend on how other finals you have, right? Like you want.
Conversation and characterization where we didn't want to overlap because we have that earlier today, that it just not happen on Tuesday because that would be.
So it's really up to the majority of you what you choose to do. If you are asking whether it's, I think you're asking whether it's Tuesday or Thursday, because it will happen presumably at our class time, for example. Yeah. Yeah.